Today's presentation is going to focus on how to increase your TUFLOW HPC model simulation speed. I'll be discussing 6 key topics today. Those include review of your domain extent, review of your minimum simulation time step, optimization of your subgrid sample distance, and also consideration of your 2D cell size, GPU hardware, and whether you can run multiple simulations on a single GPU card. To facilitate the discussion, I've established a hypothetical model, which is shown on the right here. It covers spatial area of 7 kilometers by 7 kilometers. I've modeled it at a 20-meter cell size, and I've run this model on my own laptop, which has an RTX 4060 GPU card. Also, for the purpose of the hypothetical demonstration, let's assume that the star, which is now shown on the screen, represents my area of interest. Let's say there's a hypothetical lot of land there that has a proposal for development, and I'm focused on developing a model for that assessment. The first item I'd like to bring your attention to is domain extent. It's important that you define a domain orientation and extent that nests neatly around your computational area so you can use your compute resources to the best of their ability. For the purpose of this demonstration, I've created the model on the right with the black dotted polygon representing my domain. If you're ever wanting to review your domain, I recommend importing the DOM check R file, and that will show the orientation and extent that you've specified. Now, I've updated this model using the read.js location and grid size XY commands to this extent and orientation. Now, doing so, by making this single change, I've increased my simulation speed dramatically by 1.5 times. So the simulation time has actually come down from 45 minutes to 30 minutes. And I've seriously reduced the amount of CPU RAM and GPU RAM that's required. The initial simulation required 18.8 gigs of CPU RAM. I've reduced that down to 1.9 gigs. And it also required 0.6 gigabytes of GPU RAM, and that's been reduced down to 0.06. The computer memory reduction is significant when we start to consider running multiple simulations on a single GPU card, so that'll come as the last item that I discuss. Topic number 2, minimum computed simulation time step. TUFLOW HPC includes a great feature that enables it to calculate an appropriate time step to achieve a stable solution. Now, due to the fact that the software is choosing this time step for you, review of that chosen number becomes a useful model health check option. In essence, healthy models will be able to operate at a larger time step and as such run faster than unhealthy models. I've included links to 2 useful resources here from the TUFLOW wiki. The first one explains adaptive time stepping, and the second talks through some ways that you can review your model health, and in particular time step. I'll go through a very brief demonstration of that on the coming slide. If you do want to learn more about this, I highly recommend going to one of our instructor-led training courses. It's covered in detail there over a much longer, more broader time frame than what I'll be presenting here. Okay, so step 1 is you need to turn on the time step output, and I've done that via the command map output data types == dt, and then I've also specified my other outputs. After my simulation is complete, I would typically open up my HPC DT CSV file. It is written to the log folder, which typically sits one level above your runs directory. And when I look within that file, I review the values for the calculated current number, wave celerity number, and diffusion number, and compare those numbers against the control limit for each. So the control limit for the current number would be 1, wave celerity would also be 1, and the diffusion number would be 0.3. Once I know what is the controlling parameter of those 3, I then go to the location of minimum time step, review the results that correlate to the control number, and then fix the said error. And I'd repeat that step a number of times until I get to a position where I am no longer finding any errors. Here I've opened the hpc.dt.csv file from my simulation, and I've plotted 4 of the datasets within it. The top one is dt star, and that represents the computational time step from the simulation. And you can see that it's oscillating around 0.2 of a second. The fact that it's oscillating like this makes me believe that it's quite an unhappy model. The other 3 datasets represent the 3 control numbers that I mentioned in the previous slide. So NC represents the celerity control number, NU is the current number, and ND is the diffusion number. Of these, working backwards, if ND was approaching its limit, I would be reviewing my model cell size to see if I'm using a cell size that's smaller than necessary. If NU was approaching its limit of 1, then I'd be looking to see if there were model features that were artificially creating velocities that were too high that need to be fixed. And if NC is approaching 1, which it is in this case, I'll be looking for situations where the water depth is excessively deep. So ultimately looking to see if there's topographic issues in my model. In recognition of the information that we gathered from the hpc.dt.csv file, I've opened up my minimum time step result, my flood depth result, and also my topography inputs. What we're looking at here is the minimum time step result, and I've coloured this data set from a value of 0.2, which is red, to a value of 5, which is blue. Wherever I see red is where I need to focus my efforts to identify what might be causing that minimum time step value. And that all seems to be occurring down around here. Let's now look at the flood depth in this area. I've contoured my maximum flood depth from 0 to 10, and I can see there's a large area here which has got a depth which is greater than 10 meters deep. Let's have a quick look to see what the value actually is. Oh, it's over 600 meters deep. I question the validity of that. Now, if we step back one little bit further and look at our model inputs, I can see some white space there. We've actually left out the tile that represents the elevation in that particular location. Fortunately, in preparation for this presentation, I've run a model that includes the correct DM tile in that particular location. Making that one change, let's look at my HPC DT CSV file, and my time step, which is the top graph, has increased from a value of 0.2 to just under 2 seconds. What has that done in terms of simulation speed? It's sped things up dramatically. It's decreased the simulation time from 30 minutes down to 4 minutes. So this is a great demonstration of the benefit of reviewing your time step. If you're not doing this, you should be. The next thing I'd like to talk about is subgrid sample distance. At the time of creating this presentation, using the 2025 release version of TUFLOW, the default SGS approach is method C. Now, using that approach, TUFLOW will review the input resolution of its DEM grids to identify the minimum resolution of the available grids, and it will use that value to set the SGS sample distance. If your DEM resolution is quite small, this can translate to a situation where the amount of subgrid sampling that you're applying within each cell is excessively large, so you're just increasing the computational load unnecessarily. The example I have here, the pre-sampling based on the DEM dataset sets the sample frequency to a value of 31, which is quite high. If I reduce that sample frequency down to a value of 11, which is a sample distance of 3 meters, then my model runs a reasonable amount faster, so 1.3 times faster. The CPU RAM is reduced dramatically. Now collectively, after all these changes that we've made, this model now runs 14 times faster than the first model, and the CPU RAM requirement is 50 times less. So it's a much nicer, leaner model. And I should say, with comparable results. The results haven't been compromised. The next item of discussion is 2D cell size. Here I've zoomed into my area of interest, and the question is, how small do I need to model the cell size? If you're not familiar with this topic, I strongly recommend going to the webinars page of our website and watching the cell size assumptions webinar from 2020. There'll be about an hour-long presentation that talks through this concept in detail. But very quickly, if we look at our model and we draw a cross-section through the floodplain at our area of interest, and we plot our results from various simulations that assume different cell sizes. Red is a 60 meter cell resolution, orange is 50, yellow 40, green 30, blue or light blue is 20, dark blue is 10, and purple has a 5 meter cell resolution. From this cross section we can see that the results for the purple, dark and light blue all converge to a common answer, whereas the others produce a water level that is too high. Based on this result, I'd be confident in using any of these three solutions as my model resolution. Now that being said, to date we haven't mentioned anything about run times for these various cell size assumptions. If we discount all of the model simulations that are too coarse to get an accurate result, we're left with the 20, 10 and 5 meter model, and they run in 3 minutes, 17 minutes and 163 minutes. Of those, I would be selecting the 20 meter resolution. It achieves the result I'm after, the accurate answer, in the shortest possible time. Let's now talk about computer hardware. The more powerful your computer is, the faster your simulations are going to run. Of particular relevance to TUFLOW HPC is the type of GPU card you have. If you'd like to see the performance of your GPU card relative to others available on the market, I highly recommend going to have a look at our hardware benchmarking page on the TUFLOW wiki. Let's go there together now. This is a suite of models that many of our users have run on their own hardware, and they've sent us the results which we've subsequently tabulated so we can all see how the different GPU cards and also CPU types compare. If when you're looking at the results you don't find your GPU card, please follow the steps to participate, send us your results and we'll update the result table for you. In this result table, the hardware has been listed from fastest to slowest. You can see it, there are lots of different GPU cards in the list. This is the card that I've been using for today's simulations, the RTX 4060. It ran the benchmark data set in 47 minutes, 47.6 minutes. That's a relatively average, if not slow GPU. If I was to use the top ranked GPU, it would have run the same data sets in 12 minutes. I'm often asked if you can run multiple TUFLOW HPC simulations on a single GPU card. The answer is yes, you can, though the defining factor that determines whether it's possible or not is the amount of RAM required by your model versus the amount of available memory on your computer. You can review the run statistics for your GPU card via the steps that are listed in the link that's highlighted above there. If we would do that for the model that we've been using for the rest of this presentation, the information on the left is displayed. If we zoom into the area within the pink rectangle, that's where all the useful information is. It's reporting that a single simulation is translating to 73% utilization of the GPU card, and of the 8 gigabytes of GPU RAM available, it's requiring 179. What happens if I run 2 of those simulations at the same time? One might be running the 50-year event, the other 100-year, or 1% and 2% if you're working in AEP terms. This is how the report changes. We go up to 94% utilization, and the RAM requirement doubled. How did that impact the simulation time? Okay, so running 2 simulations in parallel at the same time actually got through that project load 1.3 times faster than if I ran both of those simulations in series, one after another. So it's not a double speed up. The models will run slower, but collectively as a group you'll get through the project load much faster. That concludes my presentation today. I hope you found it useful. If you learned anything from today's content, I would highly recommend looking at our in-person training. These sorts of topics are things that we cover in all of our courses to a much greater degree of detail than what I have here. So it's a very worthwhile exercise, meeting and greeting and talking with one of our trainers. Thank you, and happy modelling.